Hello, I'm Mike McCulloch. So today I'd like to try to explain something that I just fully realized this morning. So this is quite new work. So there are still uncertainties associated with it, but you might enjoy that. So as you may know by now, the inertial mass in quantized inertia is modified following this formula. So the modified inertial mass is equal to the original one times a factor, which is 1 minus 2 times the speed of light squared divided by the acceleration of the object you're looking at times the Hubble scale, or the scale of the cavity you're in, this theta symbol here. So the interesting thing about this is that what is important here for the inertial mass is the difference between these two terms in the brackets. So in the limit, the sort of extreme behavior should appear when these two terms are more or less similar in size. They don't exactly have to be equal, but let's say similar. So let's equate them. So 1 equals 2c squared over a theta. And you can rearrange it a bit and you get the acceleration should be 2c squared over theta. And this is a very convenient formula in quantized inertia because it tells you, well, for example, it tells you what the acceleration should be at the edge of the galaxy in a different epoch. So a long time ago, the universe was smaller, so the size of the cosmos was less, so the acceleration should have been more. So I've used this before, but what occurred to me today was that it's possible to apply this to all sorts of universes, or cosmi, if you like. So I'm going to do that now. I'm going to choose a few. So first we'll consider a star at the galaxy's edge. So, but first I should say that I'm going to present it as the acceleration times theta equals 2c squared. That is what should be roughly true in quantized inertia. So for a star at the galaxy's edge, the acceleration we know is about 2 times 10 to the minus 10 meters per second, and the size of the cavity it's in, which is the whole cosmos, has the size of 8.8 times 10 to the 26 meters. So if you multiply the acceleration by the scale, you get about 10 to the 17, which is about 2c squared. So this works really well. Now for an early galaxy, and I don't know the exact numbers here, so I'm just going to make it up and check it later. At, say, redshift z is 1, the cosmos was only half the size it is today. So we can make a guess that the acceleration will be twice, so 4 times 10 to the minus 10 meters per second, and that's multiplied by 4.4 times 10 to the 26, which gives us again 10 to the 17, or 2c squared, about 2c squared. But now we can take this same thing down into the lab. So how about the thrust capacitors that have been tested in various labs to see thrust from quantized inertia? Well, these are cavities just as much as the universe is. So again, we can calculate a times theta for them. Now the acceleration of the electrons, if the electrons are tunneling across, is on the order of 10 to the power 22 meters per second, and the size of most of these cavities is about 10 micron, so 10 times 10 to the minus 6 meters. So if you multiply these two together, you get 10 to the 17, 2c squared. So that fits very nicely. But how about particle masses? So I talked about particle masses a couple of days ago, and I published a paper on them in 2016, touching on them. So how about a proton? Let's try a proton with this scheme. So the acceleration, so assuming, as I do, that the proton is caused by a trapped photon. So it's just a photon going around in a particular area. It's trapped inside a sphere, if you like, or a circle. Then you can calculate, assuming obviously it's going at the speed of light as it goes around, the acceleration, if it's going around at the proton radius, will be about 10 to the 31, and the proton radius, multiply the proton radius, you get 10 to the minus 15. We should probably have 2 times 10 to the minus 15. And then you get something like 2 times 10 to the 16, which is a little bit smaller. So it's 5 times smaller than 2c squared, but it's fairly close. So this is interesting because it shows that what's happening in all these systems is that at their boundaries, they're testing, they're being limited by quantized inertia. Not so strongly for the proton yet, but I need to work out exactly what's happening there, exactly what pathway the photon is taking. But it seems to work over a massive range of scales, from about 10 to the minus 15 meters up to the cosmic scale of 10 to the 26 meters. So this must mean something. Okay, so I hope you've enjoyed this short, and I look forward to making another one for you tomorrow.